So because of a question I was asked about after the last lecture, I want to begin by making a comment about what we discussed in the last lecture compared to a previous lecture. So in a conformal field theory in 2 dimensions, we've discussed 2 problems. One was an infinite line where we picked a segment of length L, and then we computed that the entropy was C over 3 times the logarithm of L over epsilon, where epsilon is a UV cutoff. So we computed this, but we also observed that because on dimensional grounds, S is a function only of the ratio L over epsilon, it's uniquely determined by dependence on epsilon. Just because on dimensional grounds it's a function only of the dimensionless ratio, L over epsilon. So last time there was no L, there only was epsilon. Well, if you want, we took a circle of circumference 2 pi, we divided it into 2 equal parts. Then we conformally mapped it to an infinite strip. And we put a short distance cutoff epsilon. And we computed that the entropy was C over 3 log of 1 over epsilon plus a constant. Both of these formulas involve a non-universal constant. Well, the relevant fact is that the ultraviolet divergence is local near the boundary of between the 2 regions. Here we've divided a circle into 2 parts, U and V. Here, the boundary between U and V in each case consists of 2 points, and the ultraviolet divergence is local. It just counts the number of points. So we got the same ultraviolet divergence here as here. And this answer determines this one because it's all determined up to a non-universal constant by the dependence on the cutoff. So somebody asked me afterwards why there was no L in this problem. We could have had an L in this problem. I could have divided the circle into 2 unequal bits of length L and 2 pi minus L, like so, where the UV cutoff would now be here. And if you take 2 pi much bigger than L, much bigger than epsilon, then the computation we did last time will give the same answer we had the first time. I won't show that in detail. I'll leave it as an exercise. To do this computation, you would have to use a slightly different conformal mapping from the strip to the disk than the one we used last time. You could take the conformal mapping that we did use and compose it with an SL2R transformation of the disk that maps these 2 points to these 2 points. And then you'd find, if you repeat our considerations, that you'll get the answer we had the first time with both L and epsilon. Last time, my point of view was that generalization, we didn't really have to do it explicitly, because once we know the dependence on epsilon, we know the dependence on L on dimensional grounds. If you like, the computation we did last time was similar to setting L equals pi and not worrying about the dependence on L. That's all I'll say about this. But I have one more remark I want to make before we get to the main point of today's lecture. So we divided the circle into 2 parts, and then I've claimed that there's no Hilbert space for one of the 2 parts. Well, more precisely, there's no way to write the big Hilbert space as a tensor product of Hilbert spaces for the 2 factors. Now, the conformal mapping is supposed to make that obvious. In the conformally transformed version, we're looking at quantum statistical mechanics on the infinite line at inverse temperature beta. Now, when you studied quantum statistical mechanics, what happened probably was that you considered a simple system like an ideal gas in a box. Then you computed the energy levels. After computing the energy levels, you computed the thermodynamic functions. And then they showed you, lo and behold, the thermodynamic functions have a thermodynamic limit of large volume. What they probably didn't tell you was that the Hilbert space in which you did the computation doesn't have a thermodynamic limit. They didn't tell you it did, and they didn't tell you it didn't. They just went silent on that question, I think. This is the case when I learned quantum statistical mechanics. So, you see, what would be a Hilbert space that describes a typical excitation of a thermal system in infinite volume? Well, in every box of unit length, the system might be excited by the presence of some particles because the temperature is positive. So the number of states you need to describe it per unit length is bigger than 1. Let's say, suppose you need 2 states to describe it in a distance of 1 centimeter. Then in n centimeters, you need 2 to the n states. But in infinite volume, you need uncountably many states. Because in infinite volume, we can divide it in infinitely many pieces of equal length, each of which might or might not contain a particle. So even if we idealize it and reduce the scope by assuming that each box has only 2 possible states, we'd still get 2 to the infinity, or an uncountable dimension. So the reason your textbook didn't try to describe a Hilbert space in which you could have done the infinite volume computation is that it would have had an uncountable dimension, and Hilbert spaces of uncountable dimensions are just not useful in practice. Whether your textbook said so or not, they always worked in Hilbert spaces of countable dimensions. Now, again, the physical Hilbert space on the circle has a countable dimension, so it's definitely not the tensor product of 2 factors of uncountable dimension. So there can't possibly be a formula like this. And the conformal map to the problem in quantum statistical mechanics is supposed to be making that obvious. So what we want to head for, I think, this week is to ask what happens instead and what is still true. So the main punchline will be that we can't define entropy. So this, well, okay. Let's say there are at least 2 goals. One is to understand that region U or V in this decomposition has an algebra, not a Hilbert space, and this is an exotic algebra with an infinite amount of entanglement built in. That's one goal. Second goal is to understand, so I asked what is still true, and I'll boil down what is still true to one sentence for now to state our goal. Second goal is to learn that entropy is not well defined. Entropy of a region, I should say. But relative entropy is well defined. So, well, I hope to do at least this much by Thursday. We'll see how. Sometimes it's hard to estimate how things will how long things will take. And then we're going to discuss some applications. By that time, we'll have developed the tools we need for a few applications, which will be to the Bekenstein bound. I mentioned this already, but there'll be the Bekenstein bound, the C theorem, and the ANAC. And then finally, we'll end the course with black hole thermodynamics and the generalized second law. So that's what we hope to do in the last 7 lectures. Anyway, but we'll start at the beginning. So we want to understand for today, well, you see the two problems are equivalent. A region on the circle, or equivalently the thermal field double in infinite volume. We've seen they're equivalent by conformal mapping. So we want to understand the algebra associated to the thermal field double in infinite volume. And we're going to make simply some very general comments which depend very little on what the Hamiltonian is. And the considerations are so simple in general that we can start with the simplest Hamiltonian of all, which will be 0. So we start with a spin system. Well, I can only take the Hamiltonian to be 0 for a judiciously chosen system. So you see, the considerations which told us that there's no infinite volume Hilbert space purely involve the infrared. It has nothing to do with the ultraviolet in the quantum statistical mechanical interpretation. So it would be the same if we were on a lattice. And now we're going to go to a lattice, and we'll put a spin on each site. Let's say it'll be spin 1/2. So we put a 2-dimensional Hilbert space or a qubit on each site. A qubit is just a 2-dimensional Hilbert space. And then we take the thermal field double, which means that this system is entangled with another system at some inverse temperature, beta. We start with n spins, and then we'll take n to infinity. So, as I said, the first basic case is that the Hamiltonian is 0. So that means that the thermal density matrix is a multiple of the identity. And since its trace is supposed to be 1, it'll be 2 to the minus n in the case of n spins. But what we want to do is to write down the thermal field double state, which is a purification of the thermal density matrix. And remember, the basic formula was like this. Where EI are the energy levels. But for the moment, the energies are all 0 because the Hamiltonian is 0, and the partition function is 2 to the n for n spins. So the thermal field double state, which is this, simplifies in this case it's 1 over 2 to the n over 2. Then it's a tensor product over each pair of spins. In the thermal field double state, the ith spin, we have two systems that are entangled with each other. Let's say the A system and the B system. Each system consists of n spins, and the ith spin, to make the thermal field double state, the ith spin of system A is entangled with the ith spin of system B in this particular form, except with EI equals 0. So I could write the thermal field double state like so. So this symbol represents the state in which the ith spin of system A is up along the z-axis, say. Here, the ith spin of system B is up, and here the two spins are down. So that's the thermal field double state for a system of n spins when the Hamiltonian is 0. Now, let A be any operator on the n spins of system A. The expectation value in the thermal field double state of A is, of course, equal to the trace of A times the density matrix of system A in the thermal field double state. And we decided a little while ago that the density matrix of system A, which is also the density matrix of system B, is 2 to the minus n. And therefore, the expectation value in the thermal field double state of AB, so A and B will be two operators. Maybe I'm going to call it A tilde. I've had the experience that when I call the two operators A and B, people expect, no matter how much I say otherwise, that little b is acting on system big B. So to avoid that, I'm going to call the two operators in system A and A tilde. You see, the expectation value of this product is the same as the expectation value of the same product in the opposite order. Because they're both equal to 2 to the minus n times the trace of A tilde. Hopefully that's clear. Now we take the large n limit. Adding more spins, or adding more pairs of spins, but keeping fixed the operators. Well, if I keep the operators fixed, then when I add more pairs of entangled spins, it doesn't change the expectation value of A in the thermal field double state. So the function f of A, which is the expectation value in the thermal field double state, has a large n limit. In other words, it has a thermodynamic limit. In other words, we can consider an infinite system of spins, all with 0 Hamiltonian, in the thermal field double state. And as long as A is an operator that only acts on a finite set of spins, which I took to be n, this function doesn't care how many more spins we add. Now, it has two essential properties. One is that f of AB equals f of BA. Because that was true for, well, I called it A tilde, sorry. that was true for any given n, so it's true in the large n limit. Another property which I didn't write down for finite n, but which, you see, we arranged so that the thermal field double state was a unit vector. That's what this 1 over 2 to the n over 2 does. So because the thermal field double state is normalized, f of 1 is 1. Yes?
Should we be rescaling by 2 to the n when we take the limit?
Well, no, because, well, if you like, we did it here, right? So we arranged, with this factor, we arranged so that the state is always a normalized state.
I'm just worried that the limit is 0. I can't quite see why it's not.
Well, I'm not sure which limit you're talking about. If the limit you're asking about is this one, when we add more spins, which are decoupled, since the state remains normalized, this matrix element factorizes as a matrix element in the spins A does act on times 1 and the ones it doesn't act on. And the matrix element in the spins A doesn't act on is 1. Now, alternatively, you could be asking about a formula that isn't on the blackboard right now, which is that for finite n, f of a was 2 to the minus n times the trace of a. Now, what happens is that as we add more decoupled spins, the trace of a gets bigger because the Hilbert space gets bigger, and the 2 to the minus n compensates for that. So neither of these factors has a large n limit, but the product f of a does. So to be a little bit fancy, okay. Now we can make a Hilbert space with a countable dimension in which we can discuss the infinite volume limit. So we let A0 be the algebra of all operators that act on finitely many spins. Of system A. Now, for A and A tilde in A naught, the function f of A is defined, and f of A tilde is f of A tilde A. That's true because it was true for every finite n. And if A and A tilde only act on finitely many spins, then when n is big enough, the first n spins include all the spins that A and A tilde act on. So this is a special case of what we already did, actually. Now, notice that there only are countably many operators that only act on finitely many spins. Because there's countably many ways to pick finitely many spins, and finitely many operators act once we pick the spins. So now, we define a Hilbert space, HTFD. We include all states of the form A times psi TFD, where A only acts on finitely many spins. And the inner product is well, the inner product is what it has to be. the inner product, you see, since A and A tilde only act on finitely many spins, we can do this computation for some finite n where you know what the inner products are. So I'll just write the formula in a way that makes it manifest. That inner product is just f of A tilde dagger A. And since psi TFD was the thermal field double state, that's just the excitation value of A tilde dagger A at inverse temperature beta. That notation is overkill in this example because the Hamiltonian is 0. But something like that would be true in more general examples. So in particular, these are well-defined inner products, and they obey all properties of Hilbert space inner products except completeness. So if we literally only allow the case that A acts on finitely many spins, we will not get a Hilbert space because it won't be complete. To be complete, we have to add linear combinations of these states with smaller and smaller coefficients going out to infinity. So we complete this set of states to a Hilbert space. And that Hilbert space is called the thermal field double Hilbert space, HTFD. It's of countable dimension. So what's not true is that the thermal field double state is a tensor product of two copies of the original Hilbert space. That's true only for a finite system. For infinite n, the thermal field double Hilbert space is a new animal. That's dramatically true in the case of a black hole. So those of you who have had some exposure to black hole thermodynamics know that in the black hole context, the thermal field double Hilbert space has to do with a two-sided black hole. And it's a deep puzzle how the two sides come to be connected behind the horizon. But anyway, whatever the answer to that deep puzzle is, it's very conspicuously not true that the thermal field double Hilbert space is a tensor product of two copies of anything. But as I've explained now, not the geometrical fact in the black hole case, but just the general fact that for infinite volume, the thermal field double state isn't a tensor product. That's true for elementary reasons that I've hopefully explained. Now, we've completed the set of states to a Hilbert space. But now we can complete the algebra A0 to what's called a von Neumann algebra. All that means is that, so we allow operators that can act on arbitrarily many spins, but their matrix elements act on more and more spins or smaller and smaller. So if we have a sequence of operators which are in A0, and all matrix elements exist, where psi1 and psi2 are in this thermal field double Hilbert space, then we define an operator X such that its matrix elements are given by those limits. And we say that X is in this algebra. So, in other words, we add all operators that are limits of the operators we already have that act on finitely many spins, where the notion of a limit is that all matrix elements converge. So,
can you understand like what the difference is between this naive uncountable Hilbert space and this new countable one we constructed?
well, first of all, the naive uncountable one was one-sided, right?
Sure, but I guess I could also think about
We could make it
the product
two-sided.
of 2 copies of this.
Yes. But to make the Hilbert space one-sided, you have to make it of uncountable dimension. The magic is that in the two-sided case, you can get away with the Hilbert space of countable dimension.
Yeah. Okay.
Now, that's a slightly lame answer, I admit.
Yeah, saying it's magic, but
That's a slightly lame answer. But the black hole is a dramatic case where the two-sided Hilbert space has an extremely simple but very surprising answer. So it shows that your question can't have a simple answer, really, because I can't give you a recipe other than what I've explained for building the countable dimension two-sided Hilbert space. Now, so we defined an algebra, but the algebra we've defined is exotic. This algebra A is an exotic algebra because it has a function f with f of a tilde equals f of a tilde a, and f of a equals 1. This function is usually called a trace. It obeys the algebraic properties of a trace, but it's not a trace in any Hilbert space representation. It's a renormalized trace. For finitely many spins, f of a was the multiple of an ordinary trace in a Hilbert space representation. But then we took a large n limit and the coefficient went to 0. So f of a is really a trace with an infinite factor removed, a renormalized trace. And the fact that this algebra has a trace shows that it's a new algebra that you probably haven't encountered before, except possibly if you've studied exactly this subject. So what is the infinite algebra that you know about that has a trace? Well, if you have a Hilbert space H, now if you want infinite algebra, it should be a Hilbert space of infinite dimension. Then we could let B of H be all operators. Actually, one takes all bounded operators. Here I didn't discuss that the operators were bounded because an operator acting on finitely many spins was automatically bounded. And if it isn't automatic, I should have specified we only allow limits where x is bounded. I'm not sure if it's automatic in that setup. So if you have the reason you take bounded operators when you define a von Neumann algebra is that, as you may have learned when you learned quantum mechanics, an unbounded operator is never defined in all of Hilbert space. And therefore, it's also problematical to multiply unbounded operators because they're defined on different sets of vectors. So if you want to make an algebra of operators, this is only straightforward if you consider bounded operators. So bounded operators are defined on the whole Hilbert space, and the product of two bounded operators is bounded, so there's no problem multiplying them. So the algebra of all bounded operators on H is the von Neumann algebra that underlies standard quantum mechanics. It's called a von Neumann algebra of type 1. And it has a trace, but the trace isn't defined for all elements. The trace isn't defined for all elements because, for example, the trace of the identity is infinite. Here instead, we found an algebra that has a trace, and the trace of the identity. You all let me get away with writing f of a equals 1, which was meant to be f of 1 equals 1. Sorry. Okay. It has a trace, but the trace is defined for all elements, and in particular, the trace of the identity is 1. So this algebra is probably not one you've encountered before. It's called a von Neumann algebra of type 2-1. And I think it's the first exotic von Neumann algebra that was constructed by Murray and von Neumann. Around 1940, in roughly the way I've described to you. Now, there's another kind of exotic algebra we can immediately define. We could take the tensor product of our type 2-1 algebra with this algebra B of H, where H is some other Hilbert space. I'll call it. And that makes a new algebra A hat, and you see that A hat has a trace. But it's not defined for all elements. The trace of the identity is infinite, because that's true on B of H. So it turns out that a hat is a von Neumann algebra of what's called type 2 infinity. So A and A hat are the important examples of type 2. Of type 2 algebras. But they don't arise in ordinary quantum field theory, because the Hamiltonian we used is too special. It's become clear rather recently that A and A hat can arise after coupling to gravity. But I'm not sure we'll really have a chance to describe that in this course. Now, so far, our Hamiltonian, the only Hamiltonian we've discussed is 0. Suppose we take almost any other Hamiltonian. Now, it can be very simple. For example, it could be simply the sum over all spins of a single spin Hamiltonian that's the same for all spins. Now, we can do the same thing. We can write the thermofield double state first for systems A and B of n spins. So I consider this Hamiltonian initially for a system of n spins, and then on system A, I entangle it with system B in the thermofield double state. The thermofield double state is now 1 over 1 plus lambda to the n over 2, I think. Oh, sorry. Not 1 plus lambda. In my notes, I have 1 plus lambda written, but I think it should be 1 plus e to the minus beta lambda to the n over 2. times the tensor product. Well, it's the same as before. Well, almost the same as before. This is meant to be the thermofield double state. Well, first I wrote the thermofield double state for a single Hamiltonian, a single spin with this Hamiltonian. And then I took the tensor product of n of them, and hopefully that's the correct formula.
Is there a half an exponent, or is
Oh.
so not in the position function, but in the coefficient of the state? I don't understand.
Yes, because the Hamiltonian was lambda, so the energy levels are 0 in lambda. So half the energy is lambda over 2. And this, thank you for the correction. This should be e to the minus beta lambda over 2. I think this is correct, though. Any other questions or comments? Well, now we run exactly the same story as before. We define F, so let A act on n spins of system A. Then we define a function f of A, which is the expectation value in the thermofield double state of the operator A, which is also the thermal expectation value of A at inverse temperature beta. This last formula is important because it shows that this, okay. Now I want to say that the expectation value, the function f of A has a large n limit. Where we take n to infinity and keep the operator A fixed. Now, explicitly that's true because with this very simple Hamiltonian, the spins being decoupled, when we add more spins, we don't change f of A at all. But this version of the formula shows you that the conclusion would be true for any reasonable local Hamiltonian. Since f of A is simply the thermal expectation value of the operator A, as long as expectation values have a thermodynamic limit, the function f of A has a thermodynamic limit. So I gave an example with a simple and explicitly soluble Hamiltonian, but the construction is going to work for any Hamiltonian where the thermodynamic expectation values have a large volume limit. That means any reasonable local Hamiltonian we usually study. Now, having defined the function f of A, we do the same thing as before. So first of all, for any A in the algebra A0, that's defined as before, operators on finitely many spins of system A. F of A is defined and has a limit. Well, since f of A is the thermal expectation value of A, that's no more nor less than the statement that the thermodynamic functions have a thermodynamic limit. Then we define a Hilbert space, thermofield double Hilbert space, which has a vector A psi TFD for all A in this algebra A0. And then the inner products are the same as they were before. The inner product is given by the thermal expectation value at inverse temperature beta of A tilde dagger A. So assuming the thermodynamics has a large n limit, these inner products do. And I don't even have to write anything now because we can use the previous blackboard that I didn't plan to have here at the right moment, but we do. We didn't erase it. To define the thermofield double Hilbert space, we include all states of this kind with the inner product I just defined. Then we complete it, and we get the thermofield double Hilbert space, which is a countable Hilbert space in which we can discuss the quantum statistical mechanics. And then we did erase some things. We can complete A naught to a von Neumann algebra A by including limits. We say that the limit of xi converges to x, and we include x in A, or we add x to A, if all these limits exist for all states psi1, psi2 in HTFD. There's a very important subtlety here, though. The formal procedure is the same, but A will depend on the Hamiltonian. Because the procedure to define HTFD depended on the Hamiltonian, since it depended on the thermofield double state. So, although A naught is universal and doesn't depend on the Hamiltonian, when we complete it to a von Neumann algebra, it will depend on the Hamiltonian. Now, what's different about this case from the previous case is that we got an algebra with no trace. You see, when the Hamiltonian isn't 0, f of A tilde is not equal to f of A tilde A, even for finite n, because the density matrix is not a multiple of the identity. So we get an algebra with no trace. Thank you. So, thanks for that correction. So, with any non-zero Hamiltonian, we're going to get an algebra that doesn't have a trace. It's called a von Neumann algebra of type 3. Yes?
Sorry, I have a very basic question. So
Yes.
I guess I don't fully understand. So this seems to, like, I want to understand how important it is that we're using the thermofield double to make this whole construction. It clearly is a purification of our system.
Yes.
And it does, like, in the end, give us some thermodynamic, like, limit, right? But could we have chosen a different purification? Would have we gotten the same conclusions?
Well, if we choose it, we could. We need a purification that has a large n limit if we're going to get an infinite algebra. Well, we could have, of course, chosen a different Hamiltonian and done the same thing. But we could choose a more general purification as long as the function. The key property we use is that the expectation value of an operator, a simple operator is one that acts on finitely many spins. As long as the expectation value of simple operators have a large n limit, we can make this construction and get something. It'll depend on what state we worked with, what purification we used. So without more motivation about what you want to do, I can't make a suggestion. But in principle, you're right. We didn't have to do a thermal state. Of course, thermal states are important in physics, and also the discussion last time showed that the thermal state can be related. The issue with the thermal state in the infrared is related to the UV issue in quantum field theory. So that motivated looking at the thermal case. But other cases make sense conceptually. Any other questions? Yes?
So, just to my knowledge, but so when you're dealing with like infinite Hilbert space, you cannot like make an intrinsic construction of a trace that only works finitely, so you can only hope that like inherent quantum limiting procedure. Is that the correct logic?
Well, the one that works inherently, on every Hilbert space there's a trace.
Yeah.
A projection operator into a one-dimensional subspace has trace 1.
Yeah.
Well, it has some trace, and usually you normalize the trace, so the trace of a projection operator on a one-dimensional subspace is 1.
Sure.
That's the standard trace. And as I said, you all know in infinite dimensional algebra with a trace, even if you don't use this language, the algebra of all bounded operators in Hilbert space has a trace. But that trace is not defined for all elements, because if the projection operator on a one-dimensional subspace is 1, on a two-dimensional subspace it's 2, and the identity which projects on an infinite dimensional subspace has a trace of infinity. So the example you know of an algebra with a trace, it's not defined for all elements. Instead, with the thermal field double state with zero Hamiltonian, or in other words, by looking at an infinite set of completely entangled spins, we constructed an algebra with a trace that's defined for all elements. And that was the Murray von Neumann algebra of type 2-1. The tensor product of the two gives an algebra that's said to be of type 2 infinity. But these constructions are very special because they involve starting with zero Hamiltonian. As I showed, if we start with an even slightly more generic Hamiltonian, and this one was very simple, we can do everything the same way except there will not be a trace. So we get an algebra that's said to be of type 3.
Okay, it's only that there's no trace on the full algebra.
Yes.
Okay, good.
So,
Thank you.
So on the algebra A0, we started with, well, no, there's definitely no trace. There's no well-behaved trace that you can define at all. But one statement is certainly there's no trace on the full algebra.
Okay.
Obviously, if you consider just a finite set of spins and ignore the rest of the system, you can define a trace on the operators that act just on those spins. So, now, from the explanation, you shouldn't be too surprised at the statement that in quantum field theory, we're going to get algebras of type 3. Because when we mapped the quantum field theory problem to the thermodynamic problem, the Hamiltonian we got is the Hamiltonian of a conformal field theory in one space dimension. Whatever that Hamiltonian is, it's not 0, and it's nowhere near as simple as 0. So it's not going to give the kind of special answer that leads to type 2. It will be generic enough to give type 3. It's way more generic than is needed to get type 3. And type 3 algebras are the most difficult kinds, and they're the ones that arise in quantum field theory. So I want to summarize key properties. So a type 1 algebra is the algebra of all bounded operators on some Hilbert space. So we usually often write it as B of H, bounded operators on H. It has an irreducible representation. Namely H. this is assumed in standard quantum mechanics. So quantum microstates exist, or quantum pure states exist. Which are vectors in H. We also have density matrices and entropies. And maybe I should have, in the list of properties. So, okay. Entropies, because there is a trace. Entropies depend on the existence of a trace, because the definition of the entropy is minus the trace of rho log rho. A type 2 algebra has no irreducible representation. So let me call A the algebra. If A acts on a Hilbert space, it always commutes with another type 2 algebra. For instance, in our example, we had the thermofield double system on two copies AB of the infinite spin system. Then we defined the algebra of operators on A, and it commuted with an identical algebra acting on B. In the thermofield double system, AB, we defined A acting on A, but it commuted with what we didn't discuss, another algebra, A prime, on B. And in the construction, it was obvious that A prime is of the same type as A. Everything we said about A, we could have said about A prime. So A prime is another type 2 algebra. So this statement is much stronger than saying there's no irreducible representation on a Hilbert space. Having no irreducible representation means that you only commute with C numbers. But here you commute with the whole type 2 algebra. Now, density matrices and entropies. So there's no notion of a pure state. A pure state would be a vector in an irreducible representation. But there is no irreducible representation. But density matrices make sense. Namely, so you see, if A of type 2 acts on a Hilbert space H, for instance, the thermofield double Hilbert space in the example we discussed, then for any state psi in H, there's a density matrix for some rho in the algebra. This will exist because the trace is a non-degenerate bilinear function, which I guess I failed to say before. But such a rho will exist, and therefore we can define entropies. So for type 2, there's no pure states. But yes, to density matrices. and entropies.
But is it stated that it's a Hilbert space?
What's that?
So like this, when we write it, it seems like the Hilbert space comes with the density matrix you're in. Or the state you're in.
No. The trace has nothing to do with the Hilbert space. The trace is a trace on the algebra.
All right.
So what trace is? Trace is a map from A to complex numbers. And it's non-degenerate in the sense, I'm afraid I didn't prove this in the earlier part of the lecture. Non-degenerate means that any linear function, let's say f times the algebra to complex numbers, is the trace of A times some element of the algebra. If you're given any linear function f on the algebra, f of A is the trace of AB for some B in the algebra. There are no Hilbert space states here. Trace is purely a function on the algebra. So to prove this non-degeneracy, it really comes from the fact that the thermal field double expectation values are non-degenerate. Oh, sorry. In the derivation, see, the trace of AA dagger would be the thermal expectation value of AA dagger, and it's strictly positive. That's a general fact about statistical mechanics. AA dagger is positive in every state, so when the thermal expectation value is also positive. And this positivity implies that the trace is non-degenerate. So any linear function on the algebra is the trace of AB for some algebra element. So that will imply that if the algebra acts on some Hilbert space H, and we're given a state psi in H, an example of a linear function is the expectation value of an operator in the state psi. And as I said, that will be the trace of A times something. And since that's the usual defining property of a density matrix in ordinary quantum mechanics, we might as well call that algebra element a density matrix. And having done that, we can also define an entropy. You could call it the entropy of rho, or you could call it the entropy of the state psi for the algebra A. Those are two fairly natural notations. It would be minus the trace of rho log rho. So in a type 1 algebra, we have everything you know in usual quantum mechanics. In a type 2 algebra, we're missing pure states, but we do have density matrices and entropies. I'd like to point out that that's the situation in the case of a black hole, because Hawking discovered that he could define entropies in the presence of a black hole, but no one has since succeeded in defining quantum microstates. And at least for some purposes, it now seems that physics in the field of a black hole can be described by a type 2 algebra. But for now, we're still doing ordinary quantum field theory. So I should tell you the type 3 version of this. So if A is of type 3, it has, first of all, no irreducible representation on a Hilbert space. If it acts on a Hilbert space, it always commutes with another type 3 algebra. And importantly, it has no trace. So there are no pure states, density matrices. or entropies. And this is the situation in quantum field theory when we consider two regions. So when we consider, in quantum field theory, the algebra of operators in a local region, so why is it this situation here? It's a situation here because it's generic in quantum statistical mechanics. From the discussion, you saw that to get a type 2 algebra, we had to do something weird like taking the Hamiltonian to be 0. Any more generic Hamiltonian was going to give us a type 3 algebra in quantum statistical mechanics. And by the conformal mapping, that tells us that we're getting a type 3 algebra in the case of the conformal field theory. And more generally, the quantum field theory, since near the dividing line between the two regions where the ultraviolet divergence occurs, usually the violation of conformal invariance is unimportant. Yes?
Is the non-existence of an irrep equivalent to the same as there are no pure states?
Is the non-existence of what? Sorry.
An irreducible representation.
So the question is the non-existence of an irreducible representation the same as not having pure states? It is, but it takes a little bit of discussion to prove that. Not sure if I should prove that. I think I won't. If you want to learn more about that, I'm largely following an article I wrote, which has a very long title that begins, "Why does quantum field theory in curved space make sense?" I reluctantly decided I won't be able to lecture on that in the present course because we're starting to run out of time. But the second topic is something like the end of the title, "What happens to the algebra of observables in the thermodynamic limit?" That I've been lecturing about today, and you can find more detail in the article. So I don't want to try to give a detailed answer to your question today. But existence of an irrep is the same as existence of pure states. The reason I don't want to is that I don't want to discuss abstractly what's meant by a pure state. Any other questions? Yes?
Why should we get a type 2 for a black hole? Because the Hamiltonian is 0, right?
The Hamiltonian isn't 0. It's a surprise, I think, that we get a type 2 for the black hole or de Sitter space. So maybe I'll manage to lecture about it in the last lecture in this course. We'll see. I think there is something else I want to point out about the thermofield double Hilbert space. So I make the following claim. The state psi TFD in the thermofield double Hilbert space is cyclic separating for the algebra A0 and therefore A. Remember, A0 was the algebra of finitely many spins, and A is its completion to a von Neumann algebra. If you follow the definition of cyclic separating, and we'll go over it in a second, you'll see that it's enough to check this for A0. So separating means that A psi TFD is not 0 for all A. And in fact, its norm is the thermal expectation value of A dagger A, which is positive. So since it has positive norm, it's certainly not 0. So that shows that psi TFD is a separating vector for A0, and therefore A. Remember, for A, we would just take a limit of elements of A naught. If we have a converging sequence of elements of A naught where this expectation value is positive, it will also be positive in the limit. So that's the separating property. Cyclic says that states A psi TFD are dense in HTFD. Well, that's actually how HTFD was defined. We took all the states A on psi TFD, and they had all the properties of Hilbert space except they weren't complete. So we completed them, and then HTFD was the smallest Hilbert space that contains all these states. So by definition, this set is dense in here. So the psi TFD is cyclic separating for the algebra that acts on one side of the thermofield double. I hope that reminds you of what we proved during one of the Zoom lectures, which was the Riesz-Leiter theorem. The Riesz-Leiter theorem says that if we divide space into, well, I'm dividing space, not space-time, into two regions, U and V, the space-time picture would look more like this. In the space-time picture, the two regions are space-like separated. So U is some region, the domain of dependence of U in this picture. This picture is only space. Only space because initial data can be formulated independently at different regions of space. So we'd have an algebra associated with the region U in space and a region V in space. But the space-time picture is that the algebra associated to a region U in space is really the algebra associated with its domain of dependence. Maybe I should indicate it this way. I'll call these U0 and V0. So U is the domain of dependence of U0. V is the same thing for V0. So in this setup, the Riesz-Leiter theorem says that the vacuum, this is for, well, we proved it for the vacuum of a QFT in Minkowski space. We proved that the vacuum is cyclic separating for both algebras, AU and AV. Now, of course, there's some internal consistency because in some special cases, conformal mappings relate the fact that the thermofield double state is cyclic separating in the problem of statistical mechanics to the fact that the vacuum is cyclic separating for the algebra of a region. Okay, we don't really have time to start a new topic today, so I'll just stop here and ask for questions. Yes?
The instructions that we did were all with qubits, and we showed that for a countable collection of qubits,
Yes.
basically the starting at different states, the algebra can get as bad as possible.
Yes.
But in a QFT, it seems like things could be even worse, at least naively, because space is even worse than qubits. Is it possible to get worse than that?
Well, von Neumann classified algebras as type 1, type 2, and type 3. And the modern understanding of quantum field theory is that the algebra you get, if we made a slightly more generic Hamiltonian for the spin system, then we get the same type of type 3 algebra that quantum field theory gives. Well, I describe type 3 algebra only by negatives. Anyway, at least in the world of von Neumann algebras, the answer is that nothing is worse than we ran into. But von Neumann algebras don't capture everything you might be interested in. So there might be some additional structure you're interested in where you'd say that something is worse about the quantum field theory than the statistical mechanics problem.
So
Any other questions? As far as I know, physics is never usefully done in an uncountable dimension Hilbert space. That hasn't happened yet. I can't say it won't happen, but I'm not especially expecting it.
And so this also like infinite volume, is this like the same type of construction you would do if you like want to do a continuum limit or something? Or?
If we took the if we have this infinite volume thermal system, it gives a type 3 algebra.
Yeah.
And taking its continuum limit doesn't change that picture very much. The reason it doesn't is that we're at some inverse temperature beta, and then we add high energy modes. But the very high energy modes are very unlikely to be excited. So taking the continuum limit, going to past a certain point in the UV cutoff at fixed temperature T doesn't change very much, because you only add modes that are very unlikely to be excited.
Okay, but yeah, this is the best way to do this thermodynamic construction, that we have like a natural cutoff.
At a given temperature T, the infinite volume limit is very important, but the short distance limit isn't, because the short distance modes are suppressed by the temperature. Any other questions? Yes?
Why does this type 3 or type 2 algebra always commute with another algebra?
Well, you saw it happened in the example we constructed, right?
But that is a special example, like the idea of the A and B state. I mean, when we use the infinite Hamiltonian, we can construct another type 3 algebra, right?
We could construct a different type 3 algebra, yes. It would actually be isomorphic, it turns out.
Oh,
But,
okay.
so,
So here, another type 3 algebra, it can be an isomorphic.
at least for purposes of physics, as far as it's presently understood, any generic type 3 algebra is equivalent to any other. Okay. Technically, it's hard to make predictions about what might be discovered in the future, but physics constructions till the present only use the so-called hyperfinite type 3-1 algebra. So you always get the same algebra, up to isomorphism. It's a very weak statement because there's a huge group of automorphisms of one of these algebras. I'd like to make it more obvious. Are there any more questions? Well, I want to make it more obvious that the algebra we get in the infinite volume limit depends on the Hamiltonian. So, for example, take sigma zi to be the sigma z operator of the ith spin. And now look at the limit as I goes to infinity of sigma zi. So, first of all, for a ferromagnetic Hamiltonian, the limit exists. Well, first of all, when you take the limit as you go to infinity, that just gives the thermal excitation value of the spin. For the case of a ferromagnetic Hamiltonian, the limit exists, but depends on h. If we had, for example, an anti-ferromagnetic Hamiltonian, then the limit doesn't exist. So we extended from A naught. A naught was the simple universal algebra that didn't depend on the system. Then we extended A naught to an algebra A, which is more natural for a given system, by adding limits. But the limits we added do depend on the system, as this simple example shows. The limit, when I goes to infinity of the operator sigma zi, converges to a C number for a ferromagnetic Hamiltonian, but the C number depends on the Hamiltonian. For an anti-ferromagnetic Hamiltonian, that limit does not exist. So it's really, although you can start these constructions with the simple Hamiltonian that didn't care what the system was, for an actual system, either in field theory or in statistical mechanics, usually the algebra you want is the completion that's adapted to that system. And I think I'll stop here unless that last comment raises one more quick question. In that case, I'll see you Thursday. And what we will discuss Thursday is what you can do in quantum field theory, given that the algebra is of type 3. So the goal is going to be to explain what's called, the material I'll be explaining is in sections 3 and 4 of my lecture notes on entanglement in quantum field theory. So if you want to be more prepared for Thursday's lectures, try looking at sections 3 and 4 of that article. Section 2 was on the Riesz-Leiter theorem and related topics. So we've previously discussed section 2 of that article.